cover. We're going to get through the transport layer, some application layer stuff, some troubleshooting, and some routing stuff. But so we're going to push forward here. I'm going to try and get you guys out of here about the same time. We might have to go a little bit later. It just depends how quickly we can kind of get through the rest of this material. But the transport layer, which is layer 4 of the OSI model, we don't have any devices that function at this layer, but we do have 2 primary protocols that function at this layer. TCP, which is the Transmission Control Protocol, and UDP, which is the User Datagram Protocol. So we're going to spend some time talking about those 2 protocols in this chapter. Now, the transport layer is responsible for establishing an end-to-end communication channel or an end-to-end communication session between applications, and it allows us to deliver data in a reliable fashion or an unreliable fashion. There are 2 protocols that we see at this layer, TCP, which is the Transmission Control Protocol, and UDP, which is the User Datagram Protocol. TCP is what we refer to as a connection-oriented protocol, meaning that we establish a connection from end to end prior to sending any data. It includes things like sequencing, acknowledgement numbers. A lot of our internet-based applications are going to be TCP-based. And UDP is connectionless, meaning that it has no reliability built into it. It does not establish a connection from end to end prior to sending information. A lot of our real-time applications like voice streaming or video streaming applications and some other legacy applications like SNMP, TFTP, and so on use UDP. We're going to dive into the differences between these 2 protocols as we roll through this very, very quick chapter, okay? We know that the transport layer is also responsible for something called conversation multiplexing. We talked about this on day number 1, right? Where we take large amounts of data or large conversations and we divide them up into smaller pieces, right? We divide those conversations up into smaller pieces. That's going to allow us to interleave or multiplex conversations so that every conversation gets equal access to the network. You can kind of see that depicted here in the color of conversations that you see kind of streaming out of this host. You've got your green conversation, your purple conversation, your yellow conversation, your orange conversation. That machine or that computer only has one Ethernet connection, but all of those applications that are running on that computer have to share that network resource, that data connection. So by dividing these conversations up into small pieces and by streaming or sending these individual pieces of conversation down the line, we are able to effectively allow all conversations equal access to the network. Does that make sense? All right. All right. Now TCP, which is the Transmission Control Protocol. You got a issue?
Yeah, it jumps from 264 to 323.
Uh-oh. Looks like they it looks like they bound these. Yeah, they got it kind of mixed up here. Yeah, here's 264.
Oh yeah, I see it.
They got it kind of in the, and all your notes are in there. I was going to say you can have this book, but all your notes are in there. So might have to just kind of find the page. Let's see, I can recognize it. I see it. Looks like it's all there. It's just kind of mixed up. It's not going to be that far ahead. It's probably in the same section here. Let's see. TCP,
UDP. There we go. This is the one we're on. Yeah, that's the one I just had, and it's, looks like there's about 5 or 6 pages that are the wrong order. Yeah, sorry about that.
Okay, so different applications have different requirements. TCP, for example, provides reliable communication. We're right down here, yeah. TCP provides reliable communication because with TCP we have a whole bunch of features built into it that allow us to guarantee that data is being delivered appropriately to its destination. We have sequencing, we have acknowledgements, we have buffering, we have flow control mechanisms, all kinds of pieces built into TCP to ensure reliable delivery, whereas UDP doesn't have any of those things. Now that's going to come at a cost, isn't it? Now, what's that cost going to be? Any ideas? What is the cost of all that reliability going to be? Overhead, right? A TCP header is far larger, much larger than a UDP header, and TCP transactions, TCP communication is much, much more complex than UDP communication. All right, and it says there on that second to last bullet point, there is a trade-off between the value of reliability and the burden it places on the network. Application developers choose the transport protocol based on whatever the requirements are of their individual applications. All right. Now TCP, I think they just got this flipped, so it kind of goes backwards, right? Yeah. So you have to read like a Chinese person. All right. Yeah, it looks like it just kind of goes backwards. Okay, TCP was developed way back in the day. It's RFC 793. It is a connection-oriented protocol, as I mentioned before, meaning that we have to create a session from host to host before we send information. That means that a PC that is opening up a web page from a web server is going to establish a session with that web server prior to sending or receiving information. We're not talking about routers here. We're not talking about switches, right? Because routers and switches operate at layer 2 and 3 respectively, whereas TCP is a layer 4 protocol. So we're above the routing concept. We're above the switching concept. We have reliable delivery, meaning that all data segments that are sent are acknowledged. And if a segment doesn't get acknowledged, it gets retransmitted. We have ordered reconstruction in the form of sequence numbers. Because data is being divided up into smaller pieces and sent out, it is highly possible that data is going to arrive out of order. And if that data arrives out of order, what do? We have to store that information and then reorder it before we send it up to the application. We do that through TCP through the use of sequence numbers. We have flow control mechanisms which regulate how much data is being transmitted at one time. It speeds up and slows down the conversation. And it is a stateful protocol, which means we maintain state information about each session that occurs. Now a TCP header looks like this. We've looked at data link layer headers. We've looked at IPv4 network layer headers. We've looked at IPv6 network layer headers. Now we're looking at a TCP header. You have two fields called source and destination port. All right. And by the way, we're going to learn more about port numbers in this chapter, but a port number allows us to identify the application. You know how we have the type field that allows us to identify the network layer? We have a protocol field at the network layer that allows us to identify the transport layer. Well, guess what? We have port numbers at the transport layer that allow us to identify the application. Specific applications are assigned specific port numbers. We have a 32-bit sequence number field used for ordering of the data, a 32-bit acknowledgement field used to acknowledge data. We have a header length field. What does it mean when you have a header length field? It means that the header itself can be variable in length, right? TCP header is normally 20 bytes, but it can go all the way up to 40 bytes with options. So that header length field allows us to identify the length of our TCP header. We have some flag fields. You can see the flag fields depicted at the bottom of the slide here. Reduced flag, urgent flag, ACK flag, FIN, SYN. We're going to see some of those flags as we go through the rest of the chapter. Now, it's not entirely important for you guys to understand this protocol in detail. There isn't a whole lot on the exam, of course, about TCP, and this really gets above and beyond routing, certainly above and beyond switching. But from an application perspective, it still is important to understand how TCP functions, what its general requirements are, and how it integrates into our applications. We have a window size. We'll talk about what the window size here is in a couple of slides. We have a checksum, which is like a hash, right? A CRC. We had a checksum at layer 3. We had checksums at layer 2. Well, we have a checksum at layer 4, and so on. So you can see there are quite a few fields within TCP, and all of these fields are directly related to the functionality of TCP with regard to reliability, guaranteed delivery, buffering, flow control, etc. Now, TCP is a very, very complex protocol. We're not going to get into all of those complexities. My goal in this chapter is to give you an idea of the difference between the two protocols and really give you an understanding of what the major pluses and minuses are of using each protocol. UDP, the user datagram protocol, doesn't do any of those things. In fact, in UDP, the only thing that we have are source and destination port number, a length field, and a checksum. No sequence number, no acknowledgements, no guaranteed delivery, no reliability, no flow control. Nothing, but you can see that a UDP header is significantly smaller than a TCP header. It's only 8 bytes in length, right? 16 bits is 2 bytes. We only have 4 of those 16-bit fields, which means we have 8 bytes in length. So from an overhead perspective, a UDP segment has what, 8, 16, almost 3 times less overhead, certainly 2 times less overhead than a TCP header. But we lose all of that functionality. It's connectionless. We don't establish a connection with the destination, so there's no guaranteed order of delivery. There's no guaranteed delivery at all because the receiving host does not acknowledge the receipt of information. No flow control. It's stateless, all right? But there are reasons why TCP would be used over UDP. Now let's talk a little bit about the port numbers, because this is a very, very important concept when it comes to identifying the application. And this example really does give us a good visual of why these port numbers are important. I have a PC on the left with an address of 1.5, and I've got a web server in the same subnet with an address of 1.7. I open up a web browser on that PC. and I go to 1.7, I go to, well, let's say it's serving a page. I go to 1.7. So if we look at the top conversation, the destination MAC is AC28, the source MAC is CE53. The destination IP is 1.7, the source IP is 1.5. So from a layer 2 perspective and from a layer 3 perspective, both of these conversations are the same. I opened up one web browser and went to 1.7. I opened up a second web browser and also went to 1.7. Now, when the data is being sent back to the PC, that PC needs to have a way of identifying which application window that data goes to, right? I certainly cannot do that from the layer 2 or layer 3 information because the layer 2 and layer 3 information is identical. Even the destination port number is identical. The destination port in both cases is port 80. Well, if you remember, we have two port numbers that are specified inside of UDP and TCP. You've got a source port and a destination port. So we've already determined that the destination port is 80. Why is the destination port 80? What is so significant about port 80?
HTTP traffic.
It's HTTP traffic, right. That is what we call a well-known port. And it's tied directly to HTTP. But look at the source port in this case. For the top conversation, the source port is 1305. For the bottom conversation, the source port is 1099. That is what we refer to as an ephemeral port. E-P-H-E-R-M something O-L, right? Ephemeral, M-O-R-A-L, okay? These are ephemeral ports. That means they're randomly generated port numbers. Ephemeral simply means random. So every time a workstation opens up a connection, every time a host opens up a connection, whether it's TCP or UDP, that source port is always going to be some sort of randomly generated port number. And that is the one distinguishing factor that allows the PC to know, hey, this stream goes to this application window and this stream goes to the other application window. All right? So those port numbers allow us to define the application. The port numbers allow us to define the application. Now you will have to know some port numbers for the exam. So what I've done is I've kind of given you some of the common ones. There are literally thousands and thousands of ports defined by the IANA. But these are some of the more common ones that you would have to know for the exam. Port 21 is FTP. Port 22 is SSH. Port 23 is Telnet. HTTP port 80. And let's see, 443 is HTTPS. On the UDP side, 69 is TFTP. 161 is SNMP. Notice that DNS is unique. DNS happens to use two port number, or two, both TCP and UDP, port 53. All right. Well, we know that the port number field is 16 bits. Right? It is a 16-bit field. So if I do the math, 2 to the power of 16 is 65,536. So the most number of ports that I have available to me is 65,536. Zeros inclusive, so we have to stop at 65,535. Now the box that you see at the bottom of that page describes the breakdown of these port numbers. And who manages these port numbers? Well, guess what? The IANA. The same people that manage every type of registered number on the internet. Our well-known port numbers are 0 to 1023. What are well-known port numbers? These are applications that we use every single day. Applications that are defined, that have been defined for many, many years. And these are essentially static port numbers. The example that you see above that are examples of some different static port numbers. All right? Those port numbers, those well-known port numbers can never be used as a source port for a client. They can be used as source ports for servers because the servers are the ones that are actually running those services. But for a client, those well-known port numbers are reserved. Then we have from 1024 to 49151, we have registered ports. Now this range of ports, the registered port range, can be used as a source port, but it also defines different registered applications. The IANA realized that, hey, we have a lot more than 1,023 applications that exist in the world today. So we're going to have to define a range of ports that we can use to assign to those applications so that customers or vendors can actually advertise those port numbers to their customers for security purposes and for standardization purposes and so on. So even though those registered port number ranges are used for specific applications, they can also be used as source ports. And then the last block are the dynamic private ports, which are only used as source ports. Those dynamic private ports are only used as source ports. 49,152 to 65,535. All right? All right. If you're interested in seeing what kind of ports you're utilizing on your workstation, NetStat is a way to examine those connections. By the way, NetStat will allow you to examine not only TCP connections, but also UDP connections. This is an example where we're only looking at TCP connections, but you can see what types of port numbers your machine is participating in. If you have established connections, those would be open TCP sessions. If you're listening, those would be port numbers that your machine is running, that it's waiting for connections on, and so on. Pretty useful tool in the command prompt to kind of see. And there are a bunch of different switches that you can use with NetStat to either truncate the output or have kind of a more robust or verbose output, depending on what you're trying to find. Right? NetStat has a whole bunch of different switches available to manipulate the output. All right. The three-way handshake. This is the connection establishment process within TCP. Now, I would equate this to like a telephone conversation. When I place a phone call to somebody, I dial their number, that's their destination address. The phone rings. They pick up the phone, I say, hey, it's Scott. The person on the other side says, hey, how you doing? And I say, hey, I'm doing great. That is connection establishment. That is me identifying that the person is available to communicate. They knew who I am. They know that I want to have a conversation. They're acknowledging my presence, and then we have our conversation. Okay? So the idea of a three-way handshake is to identify that the device is accepting calls to a specific port number, like port 80 or port 443, that device has the resources available to take that call, and then we're also negotiating the properties of that communication, right? We're actually negotiating the properties of that communication. UDP doesn't do that. When I have a UDP conversation, I just simply send my data. If it gets there, it gets there. If it doesn't, it doesn't. If the port's open, it's open. If it's not, it's not. If the person is ready to receive the data, they are. If they're not, they're not. All right? How does this look from a technical standpoint? It looks like 3 different transactions. All right? Number 1, the sender, which is usually a client, the receiver is usually a server, sends out a TCP SYN request. The SYN request is where the SYN flag is established. All right? And we have some sort of initial sequence number. The reason why it's listed as X here is because that initial sequence number might not be 1. It could be a different number. The receiver receives that SYN flag and says, oh, okay, you want to establish a connection with me. I'm going to go ahead and acknowledge that you want to establish a connection. So I'm going to set the ACK flag to 1. All right? And then the sender then resets the ACK flag back to 0 and still leaves the SYN flag attached. We'll see this in the next slide in actually a Wireshark capture. And then once this whole 3-step process takes place, we've now established that both clients are ready to communicate. They've negotiated things like their window size, they've negotiated their ISNs, which are the initial sequence numbers, and they're ready to talk. Let's look at what that looks like in real, with a real packet capture. So this is that 3-way handshake in Wireshark. All right. On the top left, our source port is 56159. The destination port is 80. So this is most likely a web request. The sequence number, my initial sequence number is 0. But notice the flag field, which is just below the header length. The flag field, the SYN flag is set. See in the parentheses it says SYN. I know it's kind of hard to read in your book, but it's just down there, right down here. SYN, it's the highlighted portion, okay? So that's the SYN. And then on the next datagram, which is the one coming back from the web server, the source port becomes 80, the destination port is 56159. We have an acknowledgement of 1, but notice which flags are set. The SYN flag and the ACK flag are set. Okay? Now notice on the very first datagram, so let's go back up to the first one, there was something also calculated called a window size. It's just below the highlighted portion, a window size. We're going to talk about what a window size is in the next slide. But notice that the initial window size is set to 65,535. But when the web server responds, the web server adjusts the window size to 14,600, which is in the second box, right? We don't know what that window size is yet. We're going to see that, but just remember that as we move on to the next discussion here. And then the last datagram, the ACK flag is still on, but the SYN flag is reset, and the window size has gone to 32,768, but it has a scaling factor of 8. So let me see, 32,768 times 8 is 262,144, which is what we see for the calculated window size. All right? So that is the 3-way handshake. Now, there are a couple of questions that arise from this, like, for example, why is the window size changing? What does the window size do? Why is it different from one side to the other? And so on. We'll have to take a look at that. I need to teach you guys what the window size is used for. Now, as far as session termination goes, we have a similar process to terminate TCP or UDP connections, or just TCP connections, I should say, where I send us a FIN flag, you acknowledge the FIN flag, you send a FIN flag, I acknowledge your FIN flag, and, basically we've ended the conversation. Again, back to the phone conversation, this is kind of like me saying, all right, well, I guess I'm going to head out now. I'm going to let you go. Okay, well, we'll talk to you later. All righty, bye. That's it. That's the finishing of our conversation. Okay? Now, we haven't seen the window size yet. We're going to see the window size. Let me see. Yeah, next couple of slides here. We got one more slide before we get to that. Another component of TCP is its reliability in the form of ordered delivery. If segments, certainly the segments that are being generated, are being sent in order, right? But as they pass over the network, certain segments take different paths. Some segments might have to be retransmitted. By the time those segments arrive at their destination, they might arrive out of order. So there has to be a way for us to ensure that those segments get reordered. And that's where the sequence number comes in. Remember, the sequence number was a 32-bit field, in our TCP header. The sequence number is consecutive, so it allows us to identify what order these segments go in based on that sequence number. All right? All right, the window size. The one question that we have left about TCP, what is this window size? Now remember, TCP is reliable, which means that for every segment that I send, I should be getting an acknowledgement. The problem with that approach is that it generates a lot of overhead. If I send you 20 segments, I don't want to get 20 acknowledgements. So what TCP does is it negotiates this thing called the window size. It says, you know what? I'm going to send you 10,000 bytes of data. And then you acknowledge you received that 10,000 bytes of data. It doesn't mean that I'm not sending, it doesn't mean that I'm not sending multiple segments. I still can't exceed my MTU size. But I might send you 10,000 bytes of data, and then you can send me an acknowledgement for those 10,000 bytes of data. So the larger the window size, the more efficient TCP becomes. The larger the window size, the more efficient TCP becomes, because that means I'm sending fewer acknowledgements. So if I have a window size of 3,000 bytes, for example, which we see here, that means I send you 2 segments, you acknowledge it. Once you've acknowledged the 3,000 bytes by essentially sending the next byte you expect to get, in this case 3001, I send you a couple more segments, and you acknowledge those 2 segments. Now, why in this case, if I go back here, why in this case would the client have such a large window size, but the server would have a small window size? In other words, the server is saying, only send me 14,600 bytes, whereas the client is saying, you can send me 262,144 bytes before I acknowledge. The PC is servicing itself. The web server is servicing a bunch of clients, isn't it? So it has to share those resources among multiple devices that are communicating to that web server. So naturally, the web server is a little bit more busy than the client is. It's not going to be able to handle as much data at one time. So these window sizes are not synchronous. They're asynchronous, meaning that they're different from the sender to the receiver. All right? What happens if I lose data? I send you sequence number 1. I send you sequence number 2. which is 3,000 bytes. You acknowledge 3001, which means you're telling me you got the first 3,000 bytes. I send you sequence number 3. I send you sequence number 4. Now you should be acknowledging 6001 at this point, right? Because that would be the next byte that you would expect to receive. But you don't. You acknowledge 3001. You acknowledge the same thing that you acknowledged before. That tells me that you missed a segment. Not only does it tell me you missed a segment, it tells me which segment you missed, because you missed sequence number 3001. Okay? But notice that the receiver also adjusted the window size to 1500. Meaning that send me sequence number 3001 and then I'll let you know if I got it. And certainly what happened, I sent you sequence number 3001, and what did you acknowledge? 6001. Because you did receive sequence number 4501. So that sequence number 4501 was buffered or stored, so I didn't have to retransmit both segments. I only had to retransmit one segment. So this window size will go up, it will go down, it will go up, it will go down, and this is what we call flow control. All right? The larger the window size, the more efficient the protocol.
What happened to sequence 4501? Because
It was received. It was received. And it was stored.
okay, I see.
All right? The receiver acknowledges 6001 because it's basically telling the sender, I did get the 4501 sequence. So now you can start sending me from 6001 on. Make sense?
Mm-hmm.
Of course, UDP doesn't do any of that stuff. We call this the useless datagram protocol, right? Because it doesn't have reliability, it doesn't have sequencing, it doesn't have acknowledgement numbers. It doesn't do any of this stuff. All right, TFTP, DHCP, DNS, all UDP based. If data arrives out of order, guess what? It gets sent to the application out of order. Now, it doesn't mean that that data doesn't get reordered. Usually, it's the application's responsibility to do that reordering. All right, just some port numbers that you should know. Like I said, there are some port numbers that are tested on. Port 80, HTTP, port 20 and 21, FTP, SMTP port 25, Telnet port 23, DNS port 53. Okay. These used to show up quite a bit on the old test. They don't tend to show up as much on the new test, but it doesn't hurt to know them. These are some very common, well-known port numbers. And from a UDP perspective, just a few. DHCP, port 67 and 68 in the form of something called BootP. DNS port 53, SNMP port 161, TFTP port 69. That should be the page right before that. Right. That's the last page, so you should be good to go now. Looks like they just got like 7 pages out of order or something. Okay. All right.